Hey, hello and welcome to my video about position versus time graphs. This is a position versus time graph. It measures how far away you are from some point at every second. That's why this says distance, but this says position. They're the same thing. Basically, a position is some location in the real universe. But in order to talk about a location in the real universe, we have to do it with reference to something else. So let's say that you're here. And you say, where's here? Like your friend wants to know where you are. The way that you tell them is you tell them with reference to something else. So you say, I am, maybe, here's your house. Maybe like 1 block north of my house. Or you say that I'm next to the big tree. Or you say that I am at GPS coordinates, whatever, some numbers, right? And those numbers are your location relative to the surface of the Earth. Basically, in order to talk about a position, we can only talk about it when we talk about how far it is from some other thing. So that's why I have distance here and position here. They're the same. So we're going to use this football field to determine position in this video because I figured it would be good to use something you're familiar with. We're going to pretend like this is a metric football field, though, not an imperial football field. So we're going to be using meters instead of yards, even though I know that's not really the way it works. It makes it a lot more sciencey, which is what we want. We're going to measure with reference to this line right here. The end zone, your end zone, is going to be 0 meters. So if I say that you are 10 meters, like 10 meters is your position, that means you are 10 meters away. If I say that you're 40 meters, you're 40 meters away. So this video is about learning how to use position versus time graphs and how to make them. So let's say that the football is just sitting at the 20-meter mark for 5 seconds. Just sitting there. What would the graph look like? Just sitting and sitting and sitting. Nobody's doing anything. Well, this is what it would look like. You would have your distance versus time graph. Time is in seconds, so this is at 1 second, this is at 2 seconds, 3, 4, 5. This is 10 meters, 20 meters, 30 meters, 40 meters, etc. I'm sure you get it. So where is it at the beginning, before it starts, at 0 seconds? Well, it's right there, at the 20-meter line. That's where it started, before we started the stopwatch. Okay, where was it at 1 second? Do you remember? It was at at 1 second. It was still at the 20-meter line. Nobody moved it. So where was it at 2 seconds? Same place, right? Nobody moved it. Where was it at 3 seconds? It was still at the 20-meter line. At 4 seconds, 5 seconds, 6 seconds, 7 seconds. It was the same. It's going to be the same until somebody moves it. So these are all the locations of the ball that we're sure about. We're sure it was there for the whole time. Now, for the next part of this video, I'm going to be assuming that the ball moves smoothly. But that's not important right here. I'll talk about it when I get there. Basically, it was there at 1 second and 2 seconds and 3 seconds and 4 seconds and 5 seconds. Nobody moved it anywhere else. So at half a second, it was in the same place. At 1.5 seconds, it was in the same place. 2.5 seconds, it was in the same place. Whatever. And forever. On and on and on. Until somebody moves it. The graph of the distance versus time, or the distance versus time graph will look like this. So this is supposed to let you know that a straight horizontal line on a distance versus time graph, or position versus time graph, means that an object is not moving at all. It is staying at one distance for a very long time. So I think you get that. What happens if the football starts at 20 meters, but it moves to the 50 in 2 seconds? It's not just sitting there forever. It starts at 20 meters, but then over the course of 2 seconds, it smoothly moves to the 50-meter line. Well, let's do the same kind of thing. It started at the 20, right? So before we even started the stopwatch, at 0 seconds, it's at the 20-meter line. But 2 seconds later, it's at the 50-meter line. These are the two things we know about it. And assuming that the ball moves smoothly, this is where it is at every other time. You just connect them. This is how you make the distance or position versus time graph for a moving object. A straight slanted line means that something is moving forward. If it's slanted up like this, I should say slanted up. So if it has a positive slope, I'm going to talk like that a little bit more later. But if it's a straight line slanted up, it's constantly moving forward at a smooth, steady rate. Because it used to be back here, but later it's up here. So what if the football starts at 60 meters, but it moves backwards to the 20 in 3 seconds? So it started really far up, but it moved backwards instead of forwards. How would you graph that? We'll just think of the process. At the very beginning, 0 seconds, it was at the 60. So we know for sure this is how far away it was at that time. We also know that 3 seconds later, now it's at the 20. And assuming that it moved smoothly throughout that whole thing, like it didn't go really fast at the beginning and really slow at the end, assuming it had a constant speed and went in just the one direction, this is what the distance versus time graph would look like. We take the points we know for sure, plot them out, and connect them. So the ball that was moving backwards created a downward slanted line with a negative slope. So if you have a downward slanted line, it's moving backwards. What about this? It starts at the 60. But then over the course of 2 seconds, it goes back to the 20. Then, a second later, it's at the 40, moved up smoothly. Then, it waits a second. Nothing happens for a second. Then, it goes up all the way back to the 60 in 2 seconds. What would this look like? This seems more complicated, doesn't it? But it's not really. What you do is you plot out your points. You say that the ball starts at the 60. So at 0 seconds, it's at 60 meters. Then, 2 seconds later, it's at the 20. So you put that point down here, and you connect it. We're always going to assume the ball moves smoothly, like it doesn't go really fast, then really slow, and that it doesn't go a bunch of loop-de-loops along the way. So it goes back to the 20 in 2 seconds. So that's 1 second, that's 2 seconds. Then it goes back to the 40 in 1 second, right? So 1 second later, it's at the 40. This is our point, and we just connect them with the motion line. Now, it says in 1 second, so I have 1 second gap in between this and this. Sorry, I do this at school. That's the bell. Just ignore it. So that's a 1 second gap. It's not actually at the 1 second. This was 1 second. So in 1 second means that there was a 1 second gap in between those points. Then it waits a second. So after 1 second, it's in the same place. Then it goes back to the 60 in 2 seconds. So I say 1 second, 2 seconds, and it's back up at the 60. So you connect that line there. And I'll erase all my points. This is the position versus time graph for this motion of the ball. Once again, downward means it's going backwards. Upward means it's going forwards. Straight line means it's not moving. And then upwards means it goes forward again. This is the graph. So try it yourself. What would this motion look like? Starts at the 0, moves to the 30, moves to the 40, waits 2 seconds, goes back to the 10. You should have axes like this, seconds, meters. Try to draw it out. Pause the video. This is what it would look like. What about this one? Starts at the 30, goes back to the 0, moves up to the 40, goes back to the 10, and then it waits a second. So try your own time in seconds, distance in meters. Try to make this graph yourself. There you go. Whenever it says moves backwards, you got a negative slope. Moves up, it's a positive slope. Waits, it's a straight line. What would the motion be that goes with this graph? Wait a couple seconds, pause the video. Okay. It would start at the 40 because that's where it starts. Go backwards all the way down here to 0 meters in 2 seconds. Then, move forward up to the 20 in 1 second. That's why here, 1 second later, it's at the 20. Then, I hate this thing. Waits 3 seconds. Does not move for 3 seconds and stays at the same place. So 3, I'm an idiot. Waits 2 seconds. Because it's 3 here, 5 here, so that's 1 second. That's 2 seconds. Apologies. Anyway, what about this graph? What would this look like? So there's a straight line right there, so it's not moving for 2 seconds. There we go. So it starts at the 10, does not move for 2 seconds. Then here, positive slope, positive motion. It moves up to, draw this dotted line if you can't see it, the 40. And it takes 2 seconds because it doesn't take 2 seconds. Nope. 2 and 3. It moves up in 1 second. I am an idiot. Then it goes backwards all the way back to the 10 in 1 second. And then it waits a second because that's a straight line. So that's it. Hopefully you get the hang of this. Now I want you to notice something new, right? Let's say that a ball goes 40 meters in 6 seconds. So over the course of 6 seconds, makes it all the way up here. You would start at the 0, go up to the 40 in 6 seconds, right? Let's say instead of doing it in 6 seconds, it does it in 4 seconds. Like that. Check out that snazzy animation. This is what it would look like, right? Because 4 seconds later, it's at the 40. Then finally, let's say we have a really fast ball. This one goes up in 1 second. Zip! This is what it would look like, because 1 second later, it's up at the 40. Now I want you to notice something about these lines. This red one, the slow one, is not very slanty. Hopefully you remember that's slope, right? Doesn't have a very high slope. This next one is kind of slanty. It has a pretty high slope. And then this green one, the super fast one, is very slanty. It got there really quickly. So, the amount of slant that a line has is its slope. Slow movement is a small slope. A big movement is a big slope. So try this out. Which one of these is going the fastest? Pause it for a video, or pause the video for a second if you want. This one, because it has the biggest slope. That is the slowest, and that is in the middle. This is a tricky one, because I didn't tell you about this. Let's see if you can figure it out yourself. Which one is going the fastest? Pause it for a second. Okay. This is the fastest one, because even if the slope is negative, it's going backwards very quickly. So you look at the magnitude of the slope, or just the number that goes with it. So more slanty, faster. This is the fastest, it's slowest, this is in the middle. Even if the slope is negative, the steepest slope is the fastest. Okay, we're almost done. Let's say someone is running. So test it yourself. What happened here? Did they go faster or slower? Well, it's a bigger slope, so they got faster. What about here? What happened? Well, it's a straight line, so they stopped, right? Stopped is pretty much as slow as you can get. What about here? Well, even though this is a negative slope, they're still moving again when they were stopped before, right? So, negative slope. They're going backwards, but they're still moving, so they sped up. This is the last thing we're going to do, and it's about how to combine these sort of snapshots into a smooth curve. What's happening here? Well, this is a low slope, so it's slow at the beginning. Then it gets a little faster, then even faster, then even faster, and then it's the fastest thing ever, right? So this is a graph of something speeding up. So you know the slope is getting bigger because it starts off like this and it ends up like this. What about this? Stop for a couple seconds, see if you can figure it out. Okay, so at the beginning, this little part, slope is really steep, so it's really fast. Then it slows down a little, then it slows down some more, then it slows down some more, and then it's totally stopped. So this is something slowing down because the slope is getting smaller. You should know that these lines, if you made as many of them as you wanted, you can make it a curve, a smooth curve. So this is a curvy line of something getting faster because the slope increases. This is a curvy line of something getting slower because the slope decreases. This is the same thing except they're going backwards, right? So they start off, stopped, speed up a little more, speed up a little more, and they're going really fast, but they're going really fast backwards, which is why it's negative. Sorry if I'm talking too fast. Anyway, this is something moving fast getting backwards. And then this is something slowing down but moving backwards. So it starts off fast, slows down, slows down, slows down, totally stopped. This is something slowing down and going backwards. So this is the summary of what the graphs look like moving backwards. This is the end. Now you should be able to tell me if something is going forward or backwards based on a graph. should be able to draw a graph if I tell you how it moves. You should be able to tell me how it moves if I show you a graph. You should be able to tell me which kind of thing's going fast or slow. And you should be able to tell me if things are speeding up or slowing down. If you could do all that, great. If you can't, watch the video again, do some worksheets, watch another video, come to my tutorials, do whatever you need to do.